Hello friends, and welcome to another week of e-mentoring for EE102. This week we have what I have prepared for us are just some examples of the things that we'll be looking at, because we know that examples will help us better understand some concepts. The topic for this week is topic 3, which is electric potential, capacitance and dielectric. And I am listener Nath, and I'd welcome you again. So once we are going through this session, if you have any questions or any doubts that you would like to get cleared, please feel free to interrupt in between just to get your doubts cleared, because like what I said last week, this session is for you. So we'll be looking at some examples and see how things goes. Okay. All right. So this week's example. So the first example that I have prepared for us is from the subtopic of electric potential and potential difference. Okay. So we know that positive charge is moved from point A to point B in an electric field, and the change in the potential difference is given by whatever the potential difference of B was, subtracted from whatever the potential difference of A was. Okay, so that is known as the change in potential energy. Okay. And then if you also look at some of the subtopics that we have, like electric potential, which is V, we know that V is equal to the electric potential, which is the potential energy U upon Q naught. Okay, so this is a scalar quantity, and the unit of potential is joules per coulomb, which is eventually known as voltage. Okay, and note that 1 electric volt is 1 times 1.6 times 10 to the power minus 19. Okay, and if we look at another point, which is potential difference in a uniform E, so the potential difference between any 2 points A and B in an electric field is defined by one of the formulas. Okay, so which is change in V. Okay, write it here. Which is, so change in V is equal to the voltage of B minus voltage of A. Okay, so this is the formula that we have. Okay, note that the distance usually that is between, the distance is known as S and D, which is parallel to the electric field line. Okay, so in that sense we can also say that change in V is also equal to ED cos theta. Okay, so ED cos theta. Write it here, which is, so V is equal to ED cos theta. Okay, this is theta. Okay, so these are just some general formulas that I'm going over before we actually start off with the example that I have prepared for us today. Okay, so if you look at the first question, says, so a uniform electric field of magnitude 352 volts per meter is directed in a negative y direction. The coordinates of point A are -2, -3, point B are -2, 5, and point C are 4, 5. Calculate the potential difference between VB minus VA and VC minus VA. Okay, so now it is asking us to calculate the electric potential, and like what I have stated here in this in this formula. Okay, this formula here. Okay, ED cos theta. So this is the main formula that we will be using. Okay. Now if you look at VB minus VA, so VB minus VA, this is known as the change in, which is known as the potential difference. We can find it by minus DE, minus E, S or DE cos theta. So for our case, the first one, VB minus VA, it will be minus our electric potential, our E value of E is minus 352 times 8, which is the distance between point B and point A, okay, cos 180 because they are just straight in line. Okay. Now, once we get that, when we compute, we should be able to get our answer as, so for part A will be 2,816 watts. Okay, this is for part A. And if you look at now from point A to B, okay, so from point A to B, so it will be still minus 352 times 8 cos of 0. Okay, so now note if you look at the directions, okay, so if you look at it from that point, then cos of 0, and cos of 0 is still 1. That's why you will still get 2816 but negative in front. Okay, so you will be getting negative 2816 volts. Okay, and for the third one, on VC minus VA. Okay, so for this one, first you have to find the distance between A and C. Okay, so you're going to use Pythagoras theorem. So you're going to get root of 8 squared plus 6 squared whole thing square root, which will be 10. Okay, then you will try to find at what angle are they to each other. So you're going to use SOHCAHTOA, which is tangent inverse of 6 upon 8. So you get approximately 36.8 degrees. Okay, and then so change in V is equal to minus E S cos theta. So minus 352 times 10, which is the distance between A and C, of cos of 143.16. This 143.16 comes from 180 minus 36.86, the angle that you found between them. It should still give you 2816. Okay, so note that points B and A are points. So these 2 points over here, they are known as equipotential points. Why equipotential? Because as you can see that the voltage between them is the same. Okay. Now we have learned about the potential at any point at a distance r from the point charge q and how to calculate potential difference between 2 points. Now we will learn how to find the potential due to more than one point charge. Okay, situated at a different position from the point where we wish to calculate the electric potential. Okay, so here is the solution for this question. Please see if it was not clear to you. Okay, so as you can see, it's simply explained. The main thing that we have to focus on is the formula that we use, and the angle plays a really important role in this. Okay, because once you get the angle wrong, then there's a chance that your answer will be wrong. Okay, and the next thing is, if you notice that I have just given a note on the electric potential and potential energy due to point charges. Okay, so I feel that this is really important for us. That is why I wrote this here. Okay, because this is also one of the fundamentals of the things that we are looking at to achieve our objective for this. Okay, so it says that the electric potential V at a distance r from the point charge q is given by that formula. Okay, which is 1 upon 4 pi mu naught, which is known as K, into Q upon R squared. Okay? In simple terms, that is what this formula means. And note the value of KE, it is just this one here. Okay? Note that the potential at infinity is taken as 0. Okay? So if there is no definite integral limitations, then we take potential as 0. Okay? Now the potential at some point P due to several charges is algebraic sum of potentials due to all the charges and is given by this formula. So it's the sum. Okay? K is constant in all, that's why K is out. And the number of charges that you have, that's the number of Q1 upon R1, Q2 upon R2, Q3 upon R3. You just continue to add them and sum them until I number of times. Okay? So that's the importance of that. This is what I was telling you about as well. Okay. So now on that note, let's look at an example on 2-point charges. Okay. So it says 2-point charges, each of magnitude 2 microcoulombs, are located on the x-axis. One is at x is equal to 1 and the other is x is equal to minus 1 meter. Okay, so it says determine the electric potential on the y-axis at y is equal to 0.5 meters. Okay, so what we have to do here, you note that there are 2 charges, okay, and they have 2 different distance between them. Okay, so we know, so remember the formula that we came up with earlier. Okay, so V will be equal to K and then the sum of Q over R. Okay, so it will be the charge, sum of charge over the distance or the radius that is between them. Okay, so you can see for the first one, it will be V is equal to KE sum of Q upon R1 is equal to, okay, so this is what I mean. So it will be something like this. So we will have KE and then into Q1 over R1 plus Q2 over R2. Okay. So now we have the values. Value of K is 9 times 10 to the power of 9 and Q1 charges, both charges are same. So it is 2 times 10 to the power of minus 6 and then 2 times 10 to the power of minus 6. Okay. So now the radius. So R, remember how we said R is equal to square root of x squared plus y squared putting square root. Okay, so x is given as 1 and y is given as 0.5. So we will solve that and we should get our answer as 3.22 times 10 to the power of 4 watts. Okay, so this is the answer that we expect to get from the first one. Now let's look at part 2. Okay, so part 2 it says calculate the electric potential energy on the third charge of minus 3 microcoulombs placed on the y-axis at y is equal to 0.5. Okay. So for this one, since we already have our electric potential on the y-axis, okay, so now it is asking us the electric potential energy. Now first thing that is really important is for us to know what is the formula. So the electric potential energy is equal to, okay, so the electric potential energy is equal to the charge that we have found. So let's put that as voltage, multiply it by whatever charge it is asking us to find now, which is Q3 in this case. So voltage we have already found from top, which is 3.22 times 10 to the power of 4. And the new charge that the question has given us is minus 3 times 10 to the power of minus 6. So we should come up with the answer as minus 9.65 times 10 to the power minus 2 joules. Okay. And so here's the solution in case you still did not understand what I was trying to say. Solution is given for you to understand the concept. Okay. Now let's look at another fundamental subtopic before we move on to the example. Okay, so it is about obtaining the value of electric field. Okay, we know that electric field, it deals usually its displacement and it deals with vector. Okay, 3 directions, x, y, and z. Okay, so I, j, and k represent the vectors in x, y, and z direction. Okay, so if you have to find ex, it will be dv upon dx. If you have to find ey, it will be dv upon dy. Same thing goes with ez, which will be dv upon dz. Okay, so if the electric field depends only on the radial distance r, then er will be dv upon dr. Okay, now let's look at an example which will help us understand this. Okay, now it says over a certain region of space, the electric potential is V is equal to 5x minus 3x 2y plus 2yz 2, or z squared, I guess. Okay, so it is find the expression of the x component of the electric field over the region. Okay, so the x component. Okay. So what it means is, okay, so if we look at Ex, so Ex will be minus dV upon dx. Okay, so for Ex, it will be Ex is equal to dV upon dx. Okay, so we will first differentiate V with respect to x. If we do that, so 5x becomes 5, minus 3x squared becomes minus 3x squared y becomes 6xy, and since there is no x variable in this last value, so this just becomes 0. Thus our answer becomes minus 5 plus 6xy. Okay. Now let's look at part B. So part B says find the expression of the electric field over the region. Okay, so now when it says electric field over the region, so what we have to do is the whole equation that is given, we will do that in terms of dx, then we'll differentiate in terms of dy, then we'll differentiate in terms of dz. Okay, so that is what we'll be doing. And if we differentiate with respect to y, we should get 5x. Okay, so if we differentiate with respect to x, y, and z, our final answer should be minus 5 plus 6xyi plus 3x squared minus 2z squared j plus minus 4yz k. Right? So in K, and for part C is it's a really good one as well. It says what is the magnitude of the electric field at the point P which has a coordinate of 1, 0, 2. Okay, so you know the question that we had in part B, this is just a follow-up question with the values of x, y, and z given. Okay, so wherever you see x you put 1, wherever you see y you put 0, and wherever you see z you put minus 2. Okay, so you should come up with minus 5 plus 0k, and then you find the resultant of it, which is 5 squared plus 5 squared, whole thing square root. So square root of 50, you should get somewhere around 7.07 volts per meter. Okay, so here's the solution of that question. You might have noticed that I have only put examples or exercises for this mentoring session because we will need to know how to apply the formulas that are given. Okay, so now going on to the last example that I prepared for this mentoring session. It is the electric potential due to continuous charge distribution. Okay. So this is a really common example, exam type example that I would say. We have to just know some basic formulas. So the general expression of this electric potential due to continuous charge is V is equal to KE integral of dq upon R. Okay. So uniform line charge of line. Okay. So let's look at the example. It says a uniformly charged ring. Says a uniformly charged ring of radius A carries total charge as Q and is placed as shown in figure. Okay, find the electric potential at a point P. Okay, point P on the perpendicular central axis. Okay, so now that is the question asking is to find the electric potential. Now the question is, how will we do that, or what are the fundamentals? Note, first we need to know the formulas. Like what I said earlier, R is equal to A squared plus X squared. Okay, and dV is equal to KE dq upon R. Okay, so KE, so dq upon R, to get rid of that we can integrate. Okay, so KE becomes integral of dq upon root of A squared plus X squared. So the whole thing is KE upon root of A squared plus X squared integral of dq. Integral of dq, so dq and integral can cancel, we only get left with q. So this is the general expression that is left. Okay, which is this one here. Okay. So this was just a simple example for you to know on how to really apply the basic principles that you have learned. Okay. And just a quick review on some of the things that we will be doing, and it's important for you to understand, please go over it, is about capacitors. Okay, so we really need to know what capacitors are and what they are used for. Okay, so first thing is they are used to store the charge, energy, and release through the resistor. Okay, so it kind of acts as a battery as well. Okay, and note that capacitance formula is Q is equal to C change in V. Okay. This capacitance, it is really important, so that's why I want to discuss this on one lecture on its own, I mean one mentoring session on its own. So we will look at this in depth in our next tutorial. Okay. So we hope, I hope that you have gained some knowledge on how to apply some of the things that we have looked at today, especially on these examples that I prepared. Please feel free to drop an email or post on the discussion forum on Moodle if you have any questions regarding anything that we have covered this week. Okay. Thank you very much.